In this lecture, we are going to discuss about the response of LTI systems to complex exponentials. Right? The reason is in the Fourier series, we are representing the any periodic signal in terms of its complex exponentials. Right? Now we see why we are finding the Fourier series. I told you the in Fourier series or Fourier transforms, we need to analyze the system behavior, right? System behavior. So for that reason we are finding all these Fourier series, etc. So first we will see for an input exponential what is the output, then using the Fourier series how to find the response, that is h of s generally. Now if we apply an exponential input, what is the output response we will get is the same exponential with some amplitude change, right? This is in continuous time. This is in continuous time, right? So here the LTI system response means generally we say impulse response, right? That we know already when we do convolution. Now for a discrete time, this exponential will be represented by z power n. Here s is equal to j omega, it's a complex number. Similarly x of n is equal to z power n, that is LTI system again. So same exponential we will get with some amplitude change, that is h of z. Here h of s and s is equal to j omega, complex number, z is equal to j omega, e power j omega. If we substitute e power j omega, it will become simply e power j omega n. This we know it's a complex number, complex exponential. Similarly, if s is equal to j omega, so this is also will become e power j omega t. So same as exponential, complex exponential signal here, right? Now we'll see this comment. For a complex exponential input, the output response of an LTI system is the same complex exponential with only a change in amplitude. Now we'll see proofs of this. How if I apply complex exponential, so how we are getting the same as complex exponential with some amplitude change. That we'll see on proof that we know that for any LTI system, what is the y of t output response? The convolution between x of t convolved with h of t, which is system response, right? This is the system response and this is output response, this is input response. Now what is the convolution property or convolution sum or convolution integration? So it is integration minus infinity to infinity x of tau h of t minus tau d tau. This is one way, or integration of minus infinity to infinity h of tau x of t minus tau d tau. This is the y of t. Now x of t is given. What is x of t? It is nothing but e power st. Now we need to shift this one. So from this equation it will become minus infinity to infinity h of tau x of t minus tau means e power s into t minus t tau d tau. Now e power st I can take common because it is we are differentiating integrating with respect to tau. So e power st is a common, that is a constant. E power st integration of e power minus infinity to infinity h of tau e power minus s tau d tau. This is the y of t. Now this function or this generally we say h of s, which is generally we say Laplace transform formula, right, or equation. So h of s into e power st, which is y of t, right? So this is amplitude. Generally we say it's a constant actually. So when I substitute s is equal to j omega depending on the input signal. So once we do one example, it will be very clear. So this is the proof how if I apply a exponential signal, then our output response is also exponential with some amplitude change, right? We can prove similarly for the what you call y of n, that is discrete time. Y of n is equal to x of n convolved with h of n, right? So that you proceed for that one, that is sigma k is equal to minus infinity to infinity, right, h of k x of n minus k. Now what is x of n? We know that is z power n, which is a complex exponential. So sigma k is equal to minus infinity to infinity h of k x of n minus k. So that will become z power n minus k. So again z power n, so it's k is equal to minus infinity to infinity. Summation is in terms of k. So z power n is common, so it will become k equal to minus infinity to infinity h of k z power minus k. Again I can replace this one with a h of z into z power n. So this is the output response in discrete time for a complex exponential z power n. So this is the amplitude. So generally this is a constant, right? Constant. This is exponential. So this constant, see, y of n is a response with respect to this exponential. So this generally we call it as Eigenfunction. Eigenfunction. And this constant value is called eigenvalue, right? Similarly, this one e power st is called Eigenfunction, and this constant value is called h of s eigenvalue. So maybe we may ask in gate, they may ask about this eigenfunction, eigenvalue. So that's why we are discussing now, right? So if I see some examples, suppose x of t is given as e power some j3t, right? Now, so there is a LTI system, and this is e power j3t, and we need to find this y of t, and we suppose y of t is equal to some x of t minus 3 is given, right? See, for this system response h of t should be given, right? Then only we can find. So for that reason they will give like this, y of t is equal to x of t minus 3. Now what is x of t? E power j into 3t. Now what is x of t minus 3? That is shifted version, e power j 3 into t minus 3. So what is this one? E power j 3t into e power minus 3 into 3, j 9. So this is x of t minus 3, which is nothing but y of t. So what is y of t? E power minus j 9 into e power j 3t. So this is the eigenfunction. So that is which is called x of t, right? Now what is this? This is called h of s, right? But so this, I told you s is equal to j into omega, right? Now if I substitute this s is equal to j omega, so it will become what? So h of s is equal to e power minus j 9, right? So what it can be written? E power minus j 3 into 3, right? Yes or no? See here. So from this x of e power j into 3t, from e power minus j into 3. So what is s equal to j omega? So omega equal to, we can say it's a 3. Now we got omega equal to 3. So this can be written as h of j into omega. Omega equal to 3. So h of j3 is nothing but e power minus j9, right? Or we can say j into omega. So it's a h of e power minus s into 3 also, right? So this is the h of j3. So if I want this h of s, suppose h of s is equal to what? I can make it as e power minus 3 into s, because s is equal to j3. So it will become j into 3. So it will become e power minus j9, right? So we can make like this also if they want to find what is h of s, right? So h of s is equal to simply e power minus 3s. Right? We are going to solve one more question from the discrete time. That is, y of n is given in terms of x of n plus 2 plus x of n minus 2, and x of n is given. So we need to find this h of z, right? Now from this x of n, if I equate this is j to n is equal to e power j omega n. So omega is equal to simply omega equal to 2, right? Now what is x of n plus 2? So x of n we know, that is e power j into 2n. X of n plus 2 means e power j into 2 into n plus 2. So it will become e power j 4 into e power j 2n. One equation. Similarly, x of n minus 2, so that is e power j 2 n minus 2. So it will become e power minus j4 into e power j 2n. Now on the expression y of n is equal to x of n plus 2. So this will become e power j4 into e power j 2n plus e power minus j4 into e power j 2n. That is, two signals will get two eigenfunctions. That is, this one is h1 of z and this one is h2 of z, right? So it's like a linearity property. So how many signals are there? So it will be simply added here, right? So we'll get same like this. Two functions we'll get. So what is the h1 of z? Z is equal to e power j omega, which is equal to e power j4, right? So what is omega? We have found already omega equal to 2. So omega equal to 2 means h1 of e power j2 is equal to e power j2 into 2, right? Now it's very simple now. So again, if I write h1 of e power j omega, this will become what? So e power j omega into 2 or simply z into e square, right? J into 2 or simply z square, right? Similarly, h2 of z is equal to e power minus j4. So h2 of z is equal to e power minus j4. Again I can write h2 of e power j2 is equal to e power minus j2 whole square, right? So that means what is this? We'll get z inverse 2. This is h2 of z, right? So this is eigenvalue 2 and this is eigenvalue 1, right? h1 of e power j omega or h1 of z is equal to z square, right? So this is how to do this type of exponential. Suppose in the question itself exponential function is given. Now it's very simple to analyze the response, right? We will see the Fourier series and the LTI system. Just now we have seen if you apply an exponential signal, complex exponential signal, and we will get y of t as some h of s which is constant into e power st, right? And what is h of s here? Minus infinity to infinity h of tau e power minus s tau d tau, right? Now, but what happens when you apply this x of t is a periodic signal and it can be represented by its harmonically related complex exponential. So why we need to find that one? Because I told you in the beginning of the Fourier series introduction, we will use this mathematical tool Fourier series to analyze the system response, right? That is h of t, or to find out y of t using this x of t and h of t. Now how to find these responses using Fourier series, that we have to see. And remember, h of s is the Laplace transform, or we can say h of s is equal to e power integration of minus infinity to infinity h of tau e power minus s tau into t tau. What is h of j omega? So I substitute s is equal to j omega. So minus infinity to infinity h of tau into e power minus j omega tau d tau. Now what is this h of omega is called? See, h of t is called system response. So this is called frequency response of system, right? So that means this h of t is called system response, and the system response frequency response is called h of j omega. That is j omega, we are substituting our frequency, so that's why we call frequency response of the system, right? Once we know this frequency, then to find the y of t is very easy. So how to do that one? Now if I assume this x of t can be represented by its Fourier series, something like this, k is equal to minus infinity to infinity ak into e power jk omega naught t. Now when I represent this x of t in exponential what you call harmonically related complex exponential, the y of t also can be represented by the same, because from this property, that is, if I apply the exponential signals, we will get same exponential with some constant h of s. So this y of t can be represented by h of s, or we can say h of e power j omega or h of j omega, right? So I will represent like this: h of j omega sigma k is equal to minus infinity to infinity ak e power jk omega naught t. Now in place of omega, what we need to substitute, right? See here, whatever s is here, now we are substituting in this. Now in this case, what is this here? It's nothing but this is the s. So that means this y of t will be represented like this, right? So I will write here y of t is equal to sigma k is equal to minus infinity. This h of s will, h of j omega will go inside the summation and it will become ak h of j k omega naught into e power j k omega naught t. Now if you compare this, so this is the Fourier coefficients of the y of t or output response. So ak into h of jk omega naught, right? I told you this is the constant, right? So if I substitute in place of s j into k omega naught, so this h of s will become constant value, right? So when you want to find the output response Fourier series coefficients, what we need the frequency response or the response of the system, that is h of t. So once I know h of t, by using this formula I can find the h of j omega. Then to find the y of t, so we'll use substitute here bk. So first we'll find the Fourier coefficient, then we'll substitute here, then we'll get the y of t, right? So that is the usefulness of this Fourier series. Similarly, we can solve for the discrete time Fourier series. So I will write here. So what is that? So simply here we'll use the Z transform actually. So what is y of n? Y of n is equal to, so h of z. So h of z, or we can say e power j omega into sigma k is equal to minus. So here it's not minus infinity to infinity. Here we need to summation for the one period into ak e power jk omega naught n. This is the x of t, right? Now same property like this. So it will be goes inside of this summation for mod, this period n, and here ak into h of e power jk omega naught into e power jk omega naught n. So what is this? Is the y of n. Now what is this h of e power j omega? H of, generally we say h of z is equal to, how to find this one? Sigma k is equal to minus infinity to infinity h of k and z power minus k. This is the z transform. So detail we'll see when we talk about the z transform. Then or we can say h of e power j omega is equal to, k is equal to minus infinity to infinity h of k e power minus j omega k. Again, this is called the frequency response of the system, right? Once we know the frequency response, then we can find the output response by this is multiplying with the ak is multiplied with the system response, and k is omega is equal to omega naught. So again, this is called bk, right? The output Fourier series coefficients. Now you may ask, we have taken here, this is a one period. So this period represents the either x of n or y of n. Now the system response is may be periodic, may not be periodic. So that's why we are using this z transform minus infinity to infinity, right? Now we'll see one problem on this LTI systems and Fourier series. So x of t is given as like this, which is a periodic. X of t is equal to k equal to minus 3 to 3 ak e power jk 2 pi t. So it's already written in the complex exponential. Then the Fourier coefficients are given, a0, a1 minus 1, a2 minus 2, a3 minus 3. And h of t is also given, e4 minus t u of t. Now find the output Fourier series coefficients bk. Now from this, just now we have seen what is bk. Bk is equal to ak into h of jk omega naught. First we need to find the omega naught, then h of j omega, then it's easy to find bk, right? Now what is h of j omega? So h of j omega is nothing but, so just now we have seen integration minus infinity to infinity h of tau e power minus j omega tau theta. But what is h of tau is given as e power minus t u of t. What is e power minus t? U of t means it will be 0 to infinity. So it will be like this. This is the h of t. Right? Now, what is the integration will become? It will become 0 to infinity. H of tau means e power minus tau into e power minus j omega tau theta. Now it's a simple exponential and we can get. But before that, take 0 to infinity e power minus j omega tau minus tau d2. Right? If I take tau common, so it will become minus of 1 plus j omega. So something like this. So 0 to infinity e power minus tau. If I take common, so this become 1 plus j omega d2. So e power x means e power x, that is e power minus tau into 1 plus j omega phi. I need to differentiate this one. So we'll get minus of 1 plus j omega 0 to infinity. Now if I substitute in infinity here, e power minus infinity 0 minus of, so if I substitute 0 here, it will be 1. So 1 minus of 1 plus j omega. So what is this one? Simply 1 by 1 plus j omega, which is h of j omega. Right? Now what is the fundamental frequency? So fundamental frequency omega naught is equal to, from this question, see here, jk omega naught t. What is omega naught? Simply 2 pi. So when omega naught is equal to 2 pi, then it's very easy to find the bk, that is the Fourier coefficient, that is ak into h of jk omega naught. Now first we need to find b naught. So b naught is equal to a naught into h of j 0. Now in this, so in omega place, if I substitute omega equal to 0, so what is this? A naught is given as 1. So 1 into 1 by 1 plus j into 0. So simply 1. B naught is equal to 1. Similarly, we need to find the other coefficients, b1, b minus 1, etc. So b1 is equal to a1 into h of j into, again, omega naught. Right? So here k is equal to 0 in the previous case, now k is equal to 1. So a1 means we got, so he is given as 1 by 4 into h of j omega naught. So what is j omega naught? I mean omega naught is 2 pi. So it is 1 by 1 plus j into 2 pi. So this is the b1. Similarly b minus 1. So 1 by 4 same into h of minus j omega naught. So it will become 1 by 1 minus j 2 pi and so on. So we need to find the coefficients as like this. Now again remaining parameters, that is b2. What is the b2? a2 is given as like this. See here, a2 and minus a2 is 1 by 2, a3 and minus 3. So b2 is 1 by 2 into 1 by 2 into h of j 2 omega naught. Similarly, b minus 2 is same 1 by 2 h of minus j 2 omega naught. So 1 by 2 into 1 by 1 plus j, so omega naught. So in place of omega naught, 2 omega naught. So that is 2 into 2 pi. So it will become j 4 pi. So here b minus 2 means we will get same 1 by 2 into 1 by 1 minus j 4 pi. Similarly, b3 is given a3 is given as 1 by 3 into h of j 3 omega naught. So 1 by 3 into 1 plus j 6 pi. Right? Similarly, b minus 3, a3 is given as 1 by 3. So it will become h of minus j 3 omega naught. So it will become 1 by 3 into 1 minus j 6 pi. Right? This is, now if they want to find all the Fourier coefficients, it's a lengthy procedure. So in the GATE exam, they may ask one output Fourier coefficients, either b0, bk, b1, b minus 2, etc. So what we need to find? First we need to find the h of j omega. In the exam, they may give h of j omega also. So by this equation, we need to find the output Fourier series coefficients. Suppose they ask what is the output response, or output y of t is equal to, we know sigma k is equal to minus infinity to infinity ak h of jk omega naught into e power jk omega naught t. So this is, once we know bk, then it's easy to find y of t also. So just to do the procedure as we done when we do this continuous time Fourier series, right? So we can find the y of t also. So we just multiply the h of jk omega naught, or simply frequency response. Similarly, y of n, that is for a discrete time Fourier series also.